Hello, I'm Dr. Mark Brandon Hinga. I'm a directed energy researcher at the Air Force Research Laboratory at Kirtland Air Force Base, Albuquerque, New Mexico, USA. I'm very happy to be here today presenting our research at the ION 2022 conference. My partner in this project is Dale Williams. He is a graduate student at Purdue University. The title of our research is Autonomous Cislunar Navigation Using Optical Measurements to a Lunar Landmark. The story today is about a spacecraft that gets lost in space while it's orbiting the L1 Lagrange point, and how it uses an onboard camera to take angle-only measurements to a perceived landmark on the moon so it can figure out what its position and velocity is, and to maintain this knowledge for several weeks. Here's an outline of this study performed of my custom-built C++ orbit and navigation simulator expressed in both the inertial reference frame and the circular restricted three-body problem frame, hereafter referred to as CRTBP. In this scenario, we have a spacecraft flying in a highly inclined southern halo orbit about the L1 Lagrange point, illustrated both here in the CRTBP and inertial reference frame. But the onboard computer has forgotten where it is. It doesn't know its position and velocity, but it still knows what the time is. The spacecraft is lost in space. It does not know where it is or where it is going, but the onboard optical camera sees and recognizes a crater as the Tycho Crater and knows those lunar coordinates precisely as given on board by its JPL binary ephemeris files, that is DE421. Similarly, it recognizes an asteroid, a LEO satellite, a geosatellite in the space about it, and it can look to those objects as well to navigate and figure out what its position is. But how do we do this? How do we navigate this autonomously? One possible solution is to take angle measurements to known objects in space, have a good knowledge of the spacecraft attitude, and a good knowledge, a known ephemeris, of the perceived targets that the camera sees. Here's an illustration of the inertial and CRTBP reference frames, both of which are utilized by this two-phased algorithm. In phase 1, the batch filter is applied using 10 line-of-sight unit vector measurements to a perceived target in space. The batch filter is applied and the two-body inertial frame, and its resulting solution is used as initialization of the CRTBP navigator, that is the extended Kalman filter. Here is the observation model for the navigation algorithm. If you look carefully at the sense of the arrows, the target body, in this case an asteroid, is observing the spacecraft mathematically, which is merely the camera line-of-sight unit vector, which is blue, the blue row vector, multiplied by -1. It is the small cap's red position vectors that is unknown to the spacecraft and must be estimated. The big cap, large caps, are known from the JPL binary ephemeris files, and also with the precise time known on board, we can figure out where those objects are. The spacecraft inertial velocity is then computed using the Lambert algorithm, as the line-of-sight unit vector measurements cannot observe velocity. And now we summarize the generalities of the experiments in the custom-built environment. The navigator has perfect knowledge of the force environment. That is, the force models of the navigator perfectly represent the dynamics in the environment which it's flying. We navigate off of the perceived objects in the space around the spacecraft as it travels in the approximate 8-day orbit about the L1 Lagrange point. We start the problem with the spacecraft lost in space, but it still knows what the time is. All error represented here as 0.1 degree 1 sigma error in alpha and delta is intended to represent the total accumulation of errors due to attitude, ephemeris, and timing. Note, it is assumed the target body is always in view. There's no issues with solar exclusion angles or other issues like that. The unit vector is always provided to the navigator. The target objects are these, with a cadence of measurements that span from 1 to 60 minutes. Conclusion: using a conic approximation to CRTBP motion, we can cold start a navigator lost in space well enough to achieve a warm-up after 5 days and long-term convergence after about 20 days. It's probably best to start with a LEO satellite and then switch after about 5 days to the Tycho Crater target coordinates for extended mission times. The best measurement cadence we'll declare as 1 minute, and the navigability is significantly influenced by the size of the H matrix.